So this data, and what I told you to do in the data was let mass 1 stay the same throughout all of the things, and then to slowly increment the mass of the second ball by 0.1 kilograms. So we went through all of that. I also told you to let the initial speed of mass 1 be at 1, and the initial speed, I might have had you do it at -1, it really wouldn't matter what it is. But we were keeping the initial speeds constant. Now, you might notice that I'm using U1 and 2 instead of V1 and 2, and the reason for that is I have two objects. So at every point up until this, we've had one object, and it had an initial speed and a final speed, V1 and V2, or V0 and V, whatever it was. Well, now that I have multiple objects, what you'll want to do in that event is have a different symbol for speed of the initial speed of U and V1 versus, or I'm sorry, U1 and U2 for initial speed of object 1 and object 2, and V1 and V2. This will be more obvious at a point after today why we do that, but enough of that. So given those inputs where I keep one mass the same value all the way through, and I slowly increase the other mass by a fixed amount each time, with starting velocities that are always the same starting velocity, I notice a pattern. And so one pattern is that the final speed of mass 1 keeps getting larger. Notice that it keeps going up. But the final speed of the second object, so the final speed of the object whose mass keeps getting larger, its speed keeps going down. Magnitude-wise. Okay? The negative just indicates the direction that it goes. All right? So object 1 switches directions, as does object 2, which was fairly obvious. So we have that data, and I instructed you to do changes in speed across the collision. So V1 minus U1 would be the change in speed of mass 1 before or after the collision. Its initial speed was 1, its final speed was something else. And then the same thing for that. And so what do we notice? Well, for the change in speed of V1, we notice that its change in speed keeps increasing, which is unsurprising given that its speed was increasing. And we notice that the change in speed of mass 2 is decreasing, which is unsurprising given that its final speed was decreasing. And it was always the same starting speed. So we have a pattern here, and now it comes time to the how do I encode for that. So I guess when mass 2 is greater than mass 1, that's a funny looking N. When mass 2 is greater than mass 1, what do I notice? I notice that the change in velocity for object 2 is less than the change in velocity for object 1. So what this tells me is I have an inverse variation, or an inverse proportionality. So it's probably been a while since you bothered with it, because it would have been your pre-calculus days of your math journey. But a direct proportionality, or a direct variation as it would be couched in college algebra terms, if this goes up, then that goes up. Or if this goes down, then that goes down. That's a direct proportionality, a direct variation. But if this goes up, then that goes down, and vice versa. That's an inverse proportionality. So when the changes are in the same direction, dependent changes, when the dependent thing changes in the same direction that the independent thing changes, that's a direct proportionality. And when the dependent thing changes in the opposite direction always of the independent thing, that's an inverse variation. And so recognizing that is really critical to making certain claims about these sorts of things. And so what I can say is there is, but let's, one last thing before I get to that. You might notice, at least I hope you notice, that there's something in common. The mass 2 column and this ratio column. What is a short sentence phrase that describes how these things are the same but not the same?
They're the same, just one is negative.
They are equal and opposite, which is the same as saying they're the same but one's negative. They are equal and opposite of one another. And why did I choose, well, let's be clear here, is that this column here is the same as if I did mass 2 to mass 1, right? Since mass 1 is always 1, the ratio of mass 2 to mass 1 always seems to be equal to the opposite of the ratio of the change 1 to change 2. I get that directly from the data. Now here's why would I choose to have the ratio of delta V1 to delta V2. Okay, well let's start with the brute force method, where you know that I should compute differences and ratios. Because we've done a bunch of that so far in our lawmaking game, and all of the meaningful laws are axiomatized in those ways. There's a difference and there's a ratio. So far, that's been ubiquitous to the development of the laws that we've paid attention to. So you could just say, you know what, I fully expect that I need to find as many differences as I can that are meaningful, and I need ratios of those same things. Now, obviously, you wouldn't subtract mass from velocity. That's not a meaningful difference. It can't even be done. Okay? But you could do mass ratios, mass 1 to mass 2. You could do mass 2 to mass 1. You could do the change in 1 speed to the change in 2 speed, and vice versa. And sooner or later, you'd notice that, hey, this ratio is equal to that ratio, but they're flipped. One of them's a 2 to 1, and the other one's a 1 to 2, no matter which way I do it. And you would come to the same conclusion. But it would be better if you knew why you should do change 1 to change 2. And the reason that you should do change 1 to change 2 is what we noticed here. Mass 2 greater than mass 1 means that the change in speed 2 is less than the change in speed 1, which I got to put my 1 in there. This one getting bigger means that one gets smaller. That means it's inverse, which means you would have a different ratio. All right? And so one way to look at this is that if mass 2 increases, when mass 2 increases, the change in speed 1 increases. The change in speed for object 1 is directly proportional to the increase in mass 2. And the change in speed 2 is inversely proportional to an increase in mass 2. So as mass 2 gets bigger, it gets slower, which sort of matches with what we would expect. Okay? Smaller things running into bigger things will bounce off faster because they have less resistance to motion, otherwise known as inertia, but we'll get to that in a minute. Okay, so I'm able to obtain this proportion directly from the data and proportional reasoning. It's better to do it by proportional reasoning, but you would eventually get it just by blindly comparing differences and ratios of differences until you saw that there's an equal and oppositeness to this ratio and that ratio. All right? That would eventually obtain. Now, what do we do with this? So we get the screen here. So mass 2 is to mass 1 as the opposite of change 1 is to change 2. So what can we do with this? Well, the easy, obvious thing is if I write mass 1 change in speed 1 is the negative of mass 2 change in speed 2. I have an equation that I get from this proportion. But we've not developed what is the product of mass and a change in speed. So what we've done here, we've essentially done a modern version of what Newton did when he developed his laws. Okay? And what we're staring at here is essentially a version of Newton's second law. All right? And we call this thing here a mass times a change in speed. This is called a change in momentum. It is a momentum change, if you will. And the obvious letter to choose for a change in momentum is P. Does this work here? Can't help you with that. All right. But over here on the right, I'm going to do something a little different. Instead of delta V2, I'm going to use the second zeroth law, which says that a change in speed is equal to acceleration times a change in time. So I'll write A2 times the change in time. Change in time is the same for both sides. Technically, both sides have that change in time, okay? But the time of that interaction is the time of that interaction, all right? Well, a couple of things here, and this is just sort of a feature of science. For one, this is a new product, which means give it a new label. Every time you get a new connection, you give it a new label. You don't undo the old connections. It's still delta V is A delta T, so I'm not going to undo the second zeroth law. But I have this new thing, a mass times a change in speed. What is that? Well, historically, we understood that to be momentum. That was the way that that Latin word, momenta, made sense in this context. All right? But what about this new thing? So we're going to ignore the A delta T. We already know that delta V is A delta T. But what we don't know is, what's this? What is MA? Well, most of you have had physics before. You know that force is equivalent to mass times acceleration. It's on t-shirts, bumper stickers, billboards. You saw it in your last physics class. Pretty much everybody that takes this class has had at least one physics course in high school. And so, yes, we call this force. And Newton's law, he never wrote F equals ma. Okay? But it is the case, and you'll find it in every physics textbook, force equals mass times acceleration. That is one way to parameterize the force construct, product of mass and acceleration. It's probably better to note that acceleration is directly proportional to the force and inversely proportional to the mass. Okay? And we notice this in all sorts of settings. So, for example, like if you push something, like a chair on wheels, you can give it a force and it'll go somewhere. But if somebody sits in it, if you give it that same force, it's probably not going to go as far, if it goes at all. This. That means there's a conservation of momentum, because the negative doesn't change the amount, it means the direction. It also points to an equal and oppositeness. So right out of, you shake the second law hard enough, you get the third law. That forces come in pairs. And they're always equal in magnitude and opposite in direction. All right? So he would have, like I said, written it that way, as in terms of m dv dt, and that would have come from taking m change in speed 1 equals m change in speed 2, calling this change in momentum, calling this ma delta t, okay, because that v2 delta v would change into that, and delta p per delta t, or change of momentum, time rate of change of momentum, would equal ma, which would be this thing we call force. That's how Newton wrote it. But there's two ways you could talk about it. One way to talk about momentum is how it was conserved, which is really what we noticed first. So the fact, how would that obtain? If I take, so m1 dv1 equals minus m2 dv2, which could be written as m1 a1 delta t equals the negative of m2 a2 delta t, which means f1 delta t equals minus f2 delta t, which means f1 equals minus of f2. So what this means is this force construct, this thing that was invented to describe what the connection between mass and acceleration is, that forces always come in pairs. Pairs that are equal and opposite. Equal in magnitude, opposite in direction. Direct result of the second law. Unavoidable result of the second law, which was a weird idea in Newton's time, because in Newton's time they were struggling with whether or not objects had some sort of innate force that would cause motion. People thought, well, that rock rolling down a hill is because it's got some sort of capacity to move itself. Okay, which of course was wrong. All right, rocks don't move because they feel like it. Everything moves because there's some external force on it. But what wasn't obvious is that those forces always come in pairs. So some ways to think about that. If you, like boxing, if you haul off and hit somebody in the head, you don't notice the slowdown in the punching hand as much, because it's easier to move the head that's sitting on top of the shoulders around as it is if you do a body shot. But if you haul off and hit somebody in the body, that hand's going to come to stop much quicker than it does when you hit them in the jaw, because you'll knock their jaw aside and keep going. Okay? And so why is that? Well, the body is more massive than the head. Okay? And so, and if you watch the slow motion where you can see like the jaw and the face, or if they slow it, you can see the skin, flopping around the hand and whatnot. But you can also see, if you pay attention, that the hand that's punching gets deformed in the process as well. Well, it's a glove, right? You don't see the hand. You see that glove get smashed. But the face is getting smashed, so is the glove. right? So that's one way to look at it. If we were to get a camera that could really zoom in on the surface of, say, a table, especially if it was wood or something that you could see the depression, you would actually see heavy objects pushing into the table, okay? Or maybe if you could slow it down, you might even see the table resist back a little bit. Okay, so these forces come in pairs, and in fact, everything that's resting on a table right now, it has a weight force pressing down on that table. But it must be the case that the table's pushing back, otherwise it would be falling to the ground. So the table must be pushing back just as hard as the thing on top of it is pushing down. Otherwise it would be moving. Can you think of an exception to that? So the third law, while it shakes directly out of the tree called the second law, it also makes a lot of logical sense. All right, so we get to Newton's third law. By means of the second, as well as by means of logic. It might be simpler to recognize that the first law, an object at rest will stay at rest, or an object at motion will stay in motion until it's acted upon by an outside force. All right? And so, just think of the rolling chair example. If I push a chair, it's going to roll for a while, but it's going to do what? It's going to slow down and come to a stop. And the reason for that is the force of friction. And so to summarize, when we have mdv equals another mdv, we can, if we leave this alone, knowing it's a change in momentum, we know that delta v is a delta t and ma is f, so I have minus f delta t. We call this impulse, and there's a good reason for that. Momentum is just, like I said, a Latin word that refers to what we're talking about, but this impulse thing. Why is f delta t called impulse? Well, think of, I don't know, there used to be a circus act where some fellow would get up about 30 feet high on a pole and belly flop into a foot of water. And you'd think, oh my gosh, the guy's going to die. Well, 30 feet is too much higher than 30 feet, and a foot of water isn't enough. In fact, the impact is really too much to bear, no matter how much water is beneath it, if you do a belly flop. And so the guy would put on a helmet and kind of wear a wetsuit so that the sting wasn't quite as bad, but that impulse, that initial force will be absorbed over some amount of time. And the bigger the force, the more time is needed to absorb that impulse. So, for instance, like when people die in a plane crash, they tend to not die because of the explosion. They tend to die because all of a sudden you're going 400 miles an hour, and then you're going 0 in a fraction of a second. And usually what happens is the aorta separates from the heart and just instant lights out, or something similar in your brainstem. It's the sudden change in motion that is, either you can take that much impulse, that much force during this time interval, or you can't. All right? And so that's why, airbags have to deploy in like 0.07 seconds after a certain level of collision. Because if they don't, then the impulse interaction will be your head and the steering wheel instead of your head and the airbag. And then that airbag gives you time for that force to be absorbed. and displacement, time for that displacement to give you that. But if you just run straight into the dash or the glass or the steering wheel, well, then your body's not really equipped to handle that kind of impulse, that change in momentum. All right. Now, like we showed a second ago, this boils down to the fact that F1 is the opposite of, equal and opposite of F2. It's easy to say Newton's third law. Typically, people don't believe it when they're asked questions that if you were honest, or if you were consistent with your belief that forces always come in pairs, that's one way to say what we said, meaning that they're equal in magnitude and opposite in direction. So, for example, I imagine that everybody here has driven a car, and at one point in your car driving life, a bug has hit the windshield. I'm guessing everybody has experienced that either driving or riding in a car. Now the question is, do you really believe that forces come in pairs and they're equal in magnitude, opposite in direction? What experienced more force? The bug or the car? Or were they the same force? Did the bug experience more, less, or the same force as the car? So if I look at Newton's third law and repeat it to myself, I'm like, it must be the same force. But it's hard to believe that the car experienced the same force interaction as the bug. They clearly did, because they ran into each other, which means there was a force interaction between those two things. But the car, especially if it's on cruise control, the only way your car is going to slow down noticeably is if you're in charge of the accelerator and it kind of freaks you out and you're like, whoa, what was that? It's a big juicy bug, you know. And you're like, whoa, what was that? But if you're in cruise control, you won't even notice. And typically cruise control systems are typically maintaining speed at the 1 mile an hour increment level. Maybe half of a mile an hour on some cars, if you even have a digital gauge to do that with. And so the car, but what's the difference? The car is thousands of kilograms of mass, and its speed change was in probably the 100th or 1000th of miles per hour, meters per second or whatever. The bug, however, it's probably a gram, 2 grams at most for this bug, and it might have been going a third or a fourth, fifth of the speed of the vehicle, but in an instant, in a fraction of a second, 10th of a second or less, probably 100th of a second, the bug's mass has a radical change in speed. Okay? It's going plus 20 this way, and now it's going minus 60 the other way for a change of 80. Has this massive change in speed in the opposite direction as its head goes through its rear end. Okay? And it's no longer a functioning critter. The same force, same change in momentum. The momentum change was the same. MDV of the car, that product was the same as the MDV of the bug. The masses were out of whack, and the changes in speed were inversely out of whack. And their products were the same. What this means is, besides Newton's third law, that they're equal and opposite, it also means that momentum is a conserved quantity. Meaning in any, momentum is always conserved. Sometimes that momentum is transferred to other things other than the objects in the system. For example, two cars run into each other and they collide and parts fly, screechy noises are made, metal is twisted, and there's noise associated with the collision. There's heat due to friction associated with the collision. There's deformation of both cars associated with that collision, and eventually the two objects will come to a stop. Their momentums will go to zero, usually. All right? And so a lot of that momentum went into other things than motion of the objects. The noise was motion of air particles. The heat generated by friction was motion of the particles that were cramming and scraping together. I wasn't expecting rain today. Awesome. If only I could port a video into the video of the rain, but it's raining. And in Arizona, we freak out when it rains because it doesn't do it much. So I think that's sufficient to make the case. Momentum's a conserved quantity. And the most difficult thing for people to believe about Newton's third law and the conservation of momentum is this bug on the windshield problem. Because the car doesn't seem to care about the bug hitting it. You can't detect, you can't perceive the speed change. But it's that whole idea, that's why this bullet point that I suggested earlier is so important. If you understand that the mass ratio is equal and opposite to the inverse of the change in speed ratio, you have that idea. And when you flatten that out mathematically, you must accept conservation of momentum. And if you accept conservation of momentum, you must accept Newton's third law. Those are all looped in together. And the importance of this, I mentioned it before, one of the reasons that I teach the way I teach and have you do some of the things that I have you do is because a theoretical physicist at ASU, David Hestenes, back at a time when most of you weren't born and I was a teenager, noticed and was quite frustrated, this is the 80s, that PhD candidates who had done amazing research and had insane mathematical skills, when asked questions about Newton's laws, questions like these, would get them wrong conceptually. They would never get them wrong mathematically. They would always compute it correctly. But when asked to explain it, they would tend to be wrong in one or more ways conceptually about Newton's laws. And they're about to be doctor people in physics, yet they have conceptual problems with the basics, the introductory physics. So he set out to study it, created a whole new research paradigm in physics education. All sorts of things have changed since then, and tons of people have studied it and become relatively famous in that research community, even in premier journals like Science and whatnot. So anyways, that's a wrap.